So now I want to do a quick example where I talk about just memory, or like how variables are created in memory sequentially, and also show slight differences between the stack and the heap. So the stack being variables are bound to a function's scope, and so when the function returns, the variables no longer exist. And so a basic example of this, like firstly, we'll look at just how creating a couple of variables sequentially in memory. So I'm going to go ahead and create two variables here, foo and bar, two integers. Now, they're going to get created in the order that I've written them, so foo and then bar. The compiler is going to statically allocate these to the scope, or to the stack of main, the function main. Now, looking from, we know that the stack, the first variables start with a low memory address and the memory address increases. So this means that foo's memory address is probably going to be like in hex lower than that of bar. And so what we can do to sort of check this, we'll just do a couple of print statements. We'll print the addresses of foo and bar, and then we'll show that the spacing of them in memory is just the size of foo, or it's the size of an integer. So we'll look at foo's location. So we'll say just really simply foo, and then we'll put its location, and we'll go then bar and its location, so a pointer, which is just a memory address, and we'll cover later. And so then we'll say so new line size of foo, and this will be decimal, and we'll use the size of operator to show it. So we now have we want the memory address of foo, the memory address of bar, and the size of foo. So now if we run this, or we build it and run it, we can see that this is the memory address of foo, so it's a lower value. And if we just look at the last hexadecimal character, we have the 0, and here bar, which is being created after on the stack of main, is getting a higher memory address. And this makes sense. We have like a 4-byte memory address difference here, and the size of foo being an integer is also 4 bytes. So they're getting sequentially created. Foo is ending at the 5.0 memory location, then bar is coming literally the size of foo later at the 5.4 memory location. So now, to sort of emphasize this stack and this sort of like scope, which is sort of an advanced-ish thing in C, and a really easy way of defining it is that if I create a function, so we'll get to functions in this course a little later, but what a function is just like, it'll just enter this and it'll get given a stack. And so this is the scope of the function. So we'll call my func here. It'll just do nothing but create integer my int, and we'll say, yep, cool, you equal 2. Now, I can print this here. This is not a problem at all. Wait, put in a new line, my int. And so this, or if we call the function, we'll call it after here, my func, and now we'll make and run this. We can see that our function is getting run. It's printing out my int 2, but now, like for instance, if I try and take this same print statement here and print it in my main, so after my func has, or hold on, we'll go on the other side of it. So like my func has been run, so it's going to go into this function, it's going to create my int, and it's going to print it. And now we're going to try and print it after the function's returned. And so like, you think, hey, cool, I mean, the function's been run, it's created the variable, but my compiler won't let me build. I'm getting an undeclared error. And this is purely because the function goes into, the code or the execution goes into my func, it creates the integer on the stack of this function, printf, gets executed, it prints out to the terminal, and then it returns, destroying the stack and destroying my int. So then my int doesn't exist in main because it's outside of the scope of the my func function. So that is essentially scope. And now how we could declare a variable that can be used by both is we could either, for instance, create a global variable. So we'll say my global equals 2, my int, so we'll do here, and then we can say my global and for instance we could run the same we could also print that here. And we can do this because the global variables, they're not really attached to the scope of a function, right? And so they have the scope, like a different complete scope. They have a scope sort of the program. Global variables, arguably good, bad, just choice. Multi-threaded programs, definitely not a good choice, at least just like that. But so how we could also create variables that are not really bound to a scope is that we use the heap. And so this heap is, as I was talking about earlier, this sort of memory region on a system or of a program that is controlled or is allocated using dynamic memory allocation. So this is the functions out, like asterisk alloc, all of the malloc, calloc, realloc functions that you'll find in the standard libraries. And so how we can then create, for instance, in main, a memory region that we could also use in my function, like in my func. And so we would need some sort of way of getting the reference to my func, and without going into how functions work and parameters, what I'll do is I'll just create essentially a reference to this variable, this memory region. And so we'll also go into pointers in depth a bit later, but a pointer is just a reference to a memory region. And so when you allocate some memory on the heap, it takes the next sort of free block. It says, hey, cool, I need, if I want to put an integer there, it says, hey, okay, cool, I'm going to reserve these 4 bytes, and I'll send back the memory address. And so the memory address is stored in this variable so that in my function, in main, they're not actually using a variable tied to their stacks or their scopes. They've just got a memory address, and they just go directly to that memory address and get the data that they need. So what we'll do is we'll create, this is going to be my int reference. And so we'll not reference, we're not setting anything here. So this is just going to be, because it's global, the actual reference to the integer is able to be used in my func and in main, the scope. And so we can just allocate some memory here. So I want to allocate enough memory to put an integer in it, and then I'll print the integer in my func, right? So I'll say my int reference, because if we look at, we can also look at the documentation for malloc, and we can see that it returns, oh man, so it returned return a pointer to the allocated memory, right? And so this is a pointer, and C is a reference to the memory. It's returning the memory address. And so we're going to say, okay, cool, I'm going to store the return value, the memory address, in my int reference, and we'll go malloc, and I want to allocate, if we look again at the documentation, the argument is the size, right? And so malloc function allocates size, bytes, and returns a pointer, okay? So we need to tell it how many bytes. And so the easiest way of making sure that we're writing portable code is to use the size of operator, meaning that it'll evaluate the size of an integer on the system it's running on, or given the compiler, and then it'll allocate it. So for us, we know from our example here that our integer is 4 bytes. And so what this is going to do is going to allocate 4 bytes on the heap, and it's going to store a reference to this memory location in this variable. And so right now I know, yep, okay, cool, I've allocated it. We'll just check, because if we look at for malloc again, if we go down to the return value, we'll see on error these functions return null. So I'm not expecting this to error, since my program is small and I'm definitely not running out of memory on my system, but we can just do a bit of a sanity check. So we'll say if my int reference equals null, we'll just return an error code from the program, right? We'll just return -1. So this is a memory allocation error. Okay, so after that, we know that we've got successfully allocated memory, and so then we can call my func again. Or we should probably remove it from, we'll make another function, my print func. And so in my print func, rename that again. All we're going to do is print my variable on the heap has a value of Now we'll see in a second also a reason my int, what was it called? My int reference. Okay. Now fix up this. My global undeclared. Oh, I've removed it, okay. I should just put that back in there. That was a mistake to remove. Okay. Print my func is missing a semicolon. Okay. So because I've used the malloc function, I should include standard lib, because that is where the alloc functions live. Now we'll see. Oh, this is quite nice. It's giving us 0. So if we run this again, is it giving us something else? No. Because what we're doing here is we're allocating some memory on the heap, but we're not actually setting a value to it. So we haven't said, hey, I want my variable to be 2. I'm just printing out whatever memory, whatever the variable, the random memory that we gotten given had stored in it as a value. So this sometimes can be some random number, and it usually is, unless you actually set the memory or you zero it out, meaning you set it all to zeros. But it seems in our case this has already been zeroed out. And so here, this variable is on the heap, is been allocated on the heap. And so if we look at its location, on the heap, and we'll print it's just my int reference. So this is just the memory address where it's stored at. We can see here we have foo and bar, and then we have this other. This is on the heap. So these are on the stack, and these are on the heap. So this is a stack of main, and we can see that the memory addresses are significantly different. And this is because they're getting stored in different sections of memory. So these ones are falling on the stack of main, and these ones are falling on the heap. So hopefully this sort of outlines the difference, and also the key importance is sequential, because as we move on to looking at arrays, when you do some tricky sort of structure stuff, and definitely when you're dealing with pointers, it's really important to know that you are always dealing with variables that are very much sequential in memory. And so you can just increment memory addresses to do sort of things like iterate through arrays, do all sorts of complex stuff.